Right, when we have a vector, it is possible to break a vector up into two parts or two components. The word component really means parts. So the first thing I'd like you to do in your notes is simply under the heading vector components is to write that statement down there. To illustrate what I mean, and this diagram does not have to be in your notes. Imagine you've got a picture then being held to the ceiling by these two wires. Now each of those wires is applying a force known as a tension force, that's being applied. Now that tension force has got two parts or two components. You can think of part of the tension trying to pull sideways on the picture and part of the tension pulling upwards on the picture. Those are what we refer to then as the vector components. Another example then, pulling on a lead of a dog, that force that's being applied can be thought of as having two components. And if we know the magnitude of the actual vector and the angle at which that force is being applied in this case, then we can calculate the size of these two components to see what effect there is in this case in a horizontal direction and what effect there is in a vertical direction. So as far as this diagram is concerned, nothing that you need to put into your books. All right, so this slide here illustrates how we go about calculating or working out the size of the component. If we have this vector here labeled F, then we're going to break that vector up into these two components. We've got an angle theta there. Using a little bit of simple trig, if we call that y and we call this x, then y is the opposite to the angle. So y divided by f is equal to the sine of theta. So therefore, that vertical component, when we rearrange this equation, gives us y equals f sine theta. So hence it is there. And I think if that one's sine, we could possibly guess what the other one's going to be. But just to show you, in case you can't see it, x divided by f is going to be equal to the cosine of theta. And so therefore x is equal to f cos theta, like so. Okay, now a little thing that may or may not help you. The way I remember, I don't bother doing all this trig each time I want to remember things. All I do is I say to myself that this side here is connected to the angle theta. So that's the cosine. And this side over here is separate or opposite. So it's separated from the angle. So that one's f sine theta. So hopefully you can get to the point where you can just say, oh, yep, f cos theta, f sine theta, without having to do any working. So I'd like you to please take note of the working on this page here, please. Here's a little example of a calculation then that we could do. 10,000 newtons, 23 degrees, two components, horizontal, vertical. So in terms of this roller, there is a small force trying, this one here, this vertical force, trying to lift the roller off the ground. Let's call it FV. Now it may not actually manage to lift it off the ground because of the weight of the roller is probably a lot larger than that component FV. And there is a horizontal component which is trying to drag the roller along the ground. And so what I'm suggesting to you then is all you need to do is to say, well, this side here is separate. So therefore this is 10,000 sine, I'm running out of space, sorry, theta. And you can work that one out. I'll leave you to do the calculation. And because this FH is the side that's connected to the angle, that would be 10,000 times the cosine of theta. And again, you can work out what that's equal to. All right, vector subtraction. We've mentioned in class the idea that it is possible to subtract vectors. This looks a little bit theoretical, this particular page, but we'll illustrate it with an example on the next slide. If we want to subtract vector B from vector A, effectively what we do is we add the negative of vector B. Now, in terms of vectors, if that is vector B, the negative of vector B has the same magnitude but is in the opposite direction. So instead of trying to subtract, we turn this vector around and we simply add it. All right, so we've got vector A, here it is here, and then we've got minus vector B added head to tail down here. And just like what we've done for a vector addition now, A plus the negative of B goes from the tail of the first to the head of the last. And so A minus B is not the same as A plus B. If we had had A plus B, just sketching it here, there would have been A, there would have been B, A plus B would be over there somewhere. So it's a totally different result. Different angle, different magnitude forces, or magnitude vector being produced. So if you could please note down what's on this page, and then let's illustrate that with this worked example here. A ball could be a squash ball, striking a wall, 10 meters per second, and it bounces off the wall at 10 meters per second. And you're asked to work out the change in velocity. So let's set up things here. I would strongly suggest to you that the first thing you should do is illustrate what's going on with a diagram. There's the wall. Ball comes in. Call that V initial, 10 meters per second. And it bounces off with the same speed, V final, 10 meters per second. And it's hitting the wall at 90 degrees. So that's what's going on. But that is not the vector diagram. If you're going to draw the vector diagram, and I'm just going to do this, I shouldn't really be doing this, but I think I'll just sketch it without a ruler to save me going into the part where I pull up rulers and all that sort of thing. If I want to figure out change in velocity, it's V final minus V initial. And what do we say when we want to subtract vectors? We add the negative of V initial. So V initial is 10 meters per second to the right. The negative of V initial would be 10 meters per second to the left. Remembering that there is no change in speed, because speed is a scalar, but there is a change in velocity because velocity is a vector, and if the direction of that vector changes, even though the magnitude does not change, then there is a change in velocity. So in terms of vectors, then we would draw the final velocity vector. We would take the initial velocity vector, which has now been made negative, and we'd add it head to tail. Sorry, I'll just tidy that up. And I think you can see then that the change in velocity is 20 meters per second. And it should make sense, and we can talk about this perhaps in class, it should make sense that the change in velocity would be directed away from the wall, because in this case with my diagram, the wall will exert a force away from the wall, and that's therefore the direction of the change in velocity. Let's just flip back and have a look at the second part of this. So I seem to have flipped over 2 slides here. So I've just done part A, maybe 2 slides across. The wall, if it strikes the wall at 45 degrees, yep, okay, let's just create another slide. I'm going to get rid of that. No, I won't. I will just drag that one down to there so that we're in the right order now. Okay, my apologies for that. Full screen again. So this time it's at 45 degrees. So this is part B. So let's draw our wall. Let's have the ball coming in at 45 degrees to the wall. Coming off at 45 degrees to the wall. V initial, 10 meters per second. V final, 10 meters per second. Again, that is not the vector diagram. Now, please do not, and every year I'll say this, and every year people will not listen. Do not start trying to construct your vector diagram on that. That simply illustrates what's going on. Quite separately, draw your vector diagram. So again, delta V equals V final minus V initial equals V final plus the negative of V initial. Okay, so we take V final, we draw it there, 10 meters per second. We take V initial up there. If we turn V initial around, V initial would be that, negative V initial. So we take V initial, and it's negative. So it comes up here, negative V initial. If that's 45 degrees and that's 45 degrees, that would be a right angle. So we can use Pythagoras. So our resultant, it's not very well drawn, my apologies. Our resultant will be like so, away from the wall, and we could use Pythagoras to figure out what delta V is. All right, now, so I'll leave you to do the Pythagoras, but I think you're going to get 14.1 meters per second. Again, away from the wall, because that's the direction that the wall applies the force at.